This.
Yep. Okay, so hi. I'm going to talk about some work on multi-class online learning with Bandit feedback. This is joint work with Amirreza, Shaeiri, and Hongao, Wang. So we're in the sort of standard online learning setup. There's an instance space X. It's an arbitrary non-empty set. There's a label space Y, which for most of the talk, we'll think of this as, at most, countably infinite. There's a concept class, which is just some set of functions that map X to Y. And for the purpose of this talk, it's also interesting to talk about the effective label space size, which is basically the maximum number of labels that are possible for points in the space. OK, so for a, the learning protocol here, I'm sure most of you are familiar with it. The standard full supervision, like from Littlestone in the 80s, setting for online learning, it's a game that sort of happens in rounds. On each round T, an adversary chooses a point xt in the instance space. The learner observes xt and then makes a prediction y hat t. And then the adversary chooses a true label yt. And then the algorithm gets to observe the true label yt. And that's the full supervision feedback version. In most of this talk, we'll assume the realizability assumption, which just means that for this sequence of xt, yt pairs that the adversary is generating, we'll suppose that for every finite prefix, there's a concept in the class that's correct. And then, of course, we're interested in how many mistakes does the learning algorithm make as it goes through this sequence. The variant of this that we'll be mostly interested in here is online learning with Bandit feedback. And here, the only change is that the learner doesn't get to observe the true label yt. Instead, it only observes whether or not it made a mistake. So just the indicator of the mistake. So that's much less information that it's getting back about the true label. It just knows whether it was correct or not. And so the main topic of this work is studying how learnability with Bandit feedback relates to learnability with full supervision. OK, so let's get into some of the combinatorial structures that are relevant in online learning. Namely Littlestone trees. So Littlestone tree is a binary tree. The nodes are associated with, or have associated x's from the instance space. And then the edges have associated labels from the label space. And they can be any labels and any x's. The only constraint is that the sort of sibling edges have different labels. And then the constraint here is that for every finite path from the root, there's some concept in the class that's correct along that path, just meaning that for each node x, if the path takes the right branch, then the concept should agree with that label for x. Or if it takes the left branch, it should agree with the left label for x. So for every finite path, that's has to be some concept that agrees with those labels. And then the Littlestone dimension is just the maximum possible depth of a perfect Littlestone tree for that concept class, where perfect here just means all the leaves have the same depth, and every internal node has 2 children. OK, so the classic analysis of online learning is what we'll call here uniform analysis. This is the mistake-bound framework we're all familiar with. So we'll say a concept class is uniformly learnable if there exists a finite mistake-bound M and a learning algorithm A such that for all realizable sequences, the number of mistakes is at most M. So that's kind of a classic definition. We've all studied it quite a lot. Let's see, what's known about uniform analysis. For full supervision, it's known that any concept class is uniformly learnable with full supervision if and only if the Littlestone dimension is finite. And in the Bandit feedback variant, it's known that any given concept class is uniformly learnable with Bandit feedback if and only if the Littlestone dimension is finite and the effective label space size is finite. So there's an additional constraint in the Bandit feedback setting, and the conclusion here is there is a difference between full supervision and Bandit feedback in the uniform analysis. And in particular, if you have an infinite effective label space size, the uniform analysis is just meaningless. It just says nothing is learnable. It doesn't motivate algorithm design. You can't approach like what is a good algorithm and what like or explore this problem at all using this definition of uniform learnability. Like even for just like constant functions or something simple like this, you can't do anything. So what we're going to look at in this work is an alternative perspective that allows us to have a reasonable discussion about how to approach Bandit online learning with Bandit feedback, particularly with infinite effective label spaces. So this alternative perspective is the universal analysis. Universal referring to like the universal quantifier. So we say a concept class C is universally learnable if there exists a learning algorithm such that for all realizable sequences, it makes a finite number of mistakes. So we're not requiring a uniform bound on the number of mistakes. The number of mistakes could depend on what particular sequence we're playing with. Okay, so that's the definition. Let's look at what's known about universal learnability. In the full supervision setting, we know that a concept class is universally learnable with full supervision if and only if there does not exist an infinite perfect Littlestone tree, right? So which is a little different than infinite Littlestone dimension. It's actually much stronger to have an infinite Littlestone tree than just an infinite Littlestone dimension. Okay, so that's full supervision. Let's take a look at Bandit feedback. This is the new result in this work. What we find is that, again, a concept class is universally learnable with Bandit feedback if and only if there does not exist an infinite perfect Littlestone tree. So it's the exact same criterion for both. And so the conclusion here is that universal learnability with Bandit feedback is actually equivalent to universal learnability with full supervision. And what's nice about that is that, like in the cases of infinite effective label space size, you can still have a very reasonable discussion about how to design good algorithms for the Bandit feedback setting. So it sort of motivates algorithm design in a way that uniform analysis is not capable of doing. Okay, so let's go through the proof. The necessity side just follows from full supervision. So Bandit feedback is just harder than full supervision. So we don't have to reprove that. We actually in the paper give 3 different proofs of the sufficiency of not having an infinite Littlestone tree. So I'll just present the simplest one here, and I'll mention the bullet points of the others at the end. Okay, so here's the simplest proof. So suppose that you have a concept class that has no infinite perfect Littlestone tree. Then we know from the previous works that in the full supervision setting, there is an algorithm that guarantees finite mistakes on all realizable sequences. This is something called the multiclass ordinal SOA. Let's call that A0 here. And what we'll do is define some experts based on A0. So specifically for every finite index set, J, and for every function that maps J to the labels, so we associate a sequence of labels with the indices in J. Let's define an expert, which just produces a sequence of labels by the definition here. So if at each time t, if t is one of the special times in the set J, then the expert just gives the g of t label that's associated with that time. Otherwise, it gives the output of A0 when you feed it a history that's the xt's, the x's up to that time t, and the labels, just the expert's labels. So we're not even looking at any information about the true labels here. We're just generating based on the x's, and then we're sort of remembering what that expert did in the past and feeding it into the A0 algorithm as the labels. So why do we care about these experts? Well, here's the claim. So for any realizable sequence, there exists a J star G star such that that expert is associated with J star G star is correct on the whole sequence. And the proof is pretty simple. It's just we know this A0 algorithm makes a finite number of mistakes if it were to see the true labels. So let's let J be the times when it would make mistakes, and let G of T for each of those times be the true label. And now this A0 is always getting as input true labels. And so just sort of inductively, we conclude that the sequence is always just producing the true labels. So there exists this J star G star. We're not saying that we have some way of anticipating where it is, but we can design an algorithm based on the fact that this exists. So here's the algorithm. So let's first notice we only have a countable number of these experts, right? They're finite subsets of the natural numbers. And then labelings, there's only a countable number of labels. So there's only a countable number of these experts. And so let's just enumerate them, give them each an index I. And so what we'll do is start with the first one, the expert 1. And we'll start predicting just using that expert's predictions until it makes a mistake. And then we move to the second expert. And we keep on going and predicting using the second expert until it makes a mistake. And then, so each time it makes a mistake, we're incrementing I by 1. And then just notice that I is counting how many mistakes we're making. And of course, we'll never move past the index of that J star G star, which doesn't make any mistakes. So that guarantees we'll make a finite number of mistakes overall. So that's the whole proof. I'll just mention a couple of other results that are in the paper. As I mentioned, we actually give 3 proofs of this sufficiency. We have another one that's based on a variant of an algorithm of Phil Long, which uses the majority, the weighted majority algorithm using like a branching set of experts based on the SOA. And we do this for the universal setting, end up with like infinite branching in the end, but the analysis still works out for the universal setting. We also give an analysis of the game itself and sort of come out with like what is the game tree, what are the winning conditions of the adversary and of the learner. And this gives rise to an interesting structure we call the universal Bandit Littlestone tree, which differs a little bit from Bandit Littlestone trees, if you're familiar with those. It also reveals something interesting about like everything that we talked about was with countable label spaces. Well, it turns out if you have an uncountable label space, you get back the negative result that nothing is universally learnable with Bandit feedback. So I don't know, maybe there's another even more interesting perspective where that's not true anymore. We also extend everything to the agnostic case. We get the same theorem. No infinite Littlestone tree characterizes no regret learnability. And it's actually even a very similar proof, except instead of using this simple, we use the same set of experts, except now we have to use an algorithm called EXPINF, which is some variant of EXP3 that handles an infinite number of arms, which in this case are just the experts. OK, thanks.
I'm not an expert of universal learning, but so it seems like now universal learning is equivalent to the Littlestone dimension being finite, whatever the feedback nature is. Like whatever, if you have full information, full supervision or bandit feedback, it's uniformly, like your C is universally learnable if and only if the Littlestone tree has a finite dimension.
Is a slight difference between having a finite dimension and not having an infinite tree. So there are classes that have larger and larger finite Littlestone trees. So that would have an infinite Littlestone dimension, but maybe no single infinite tree.
Right.
So there's a lot of constructions of these kinds of classes. So our condition is just that there is no infinite tree.
There is no infinite tree. Okay,
yes.
Thanks. And does it imply anything about like the hardness? Like, is there? I mean, like maybe it's beyond, but does it imply anything on the hardness of learning in either of those settings? Like it seems like Bandit is like, or at least it's no longer visible that a Bandit would be harder than full supervision.
In a computational sense of hardness, or what?
Yeah.
Yeah. So, I guess. I mean, okay. So there's a maybe one answer is you could, okay, this reduction, which just uses the full supervision algorithm, you could do this in polynomial time as a polynomial reduction. It just sort of, you're just on the fly when you update I, figure out what the next expert in the sequence would be. So you could do this in polynomial time. There is sort of the quantification of how many mistakes are you going to make, and that may be, I'm not sure whether or how you would want that to enter into the running time analysis. Yeah, so we haven't really done running time analysis much for universal rates, and whether there's an appropriate way to formulate that. I mean, if you just want it as a function of time, this would be fine. That's an efficient reduction.
Thanks. Are there other questions? Over there.
Thank you. I have two questions, in fact. One is, which other setting would you consider then after the universal setting? Is there something else that you have in mind? Then the second question I have, okay, that was quick. Second question.
I don't have, something that would go beyond universal, because we have this result at the end that uncountable effective table space size, it also recovers the negative result. So sort of we've just shifted up a
No, but is there some sort of an intermediate setup between universal and non-universal? Is there something else that you can?
There are a couple. So universal is for all sequences of XY pairs. So there's the non-uniform setting, which is for all. Let's see, how does it work? You allow for all target concepts. But then it's uniformly quantified over the choice of sequence. That turns out to be equivalent to just a countable union of Littlestone classes. And then there's another variant which we've been talking about where you do the other quantification, like uniform over concepts, non-uniform over sequences of X's.
That sounds good. Thank you.
Thank you again, Steve.
Okay.